All right, in this next video, we're going to look at kind of the most popular and most important application of derivatives, which is position, velocity, and acceleration. All right, so this is a physics application of derivatives. All right, that's exactly what I said. All right, so imagine we have this function p of t, which gives the position of your car in miles, t hours after the start of the drive. So we think back to our last video. The thing that's going in is t, which is the number of hours. And the thing we're getting out is the position, which is miles. Right? So the derivative, what are the units for the derivative going to be? They're going to be the output unit, miles, divided by the input unit, hours. And if we say it with the division bar, this is miles per hour. Right? And if you're talking about a car and your unit is miles per hour, that's how fast you're driving. So how fast I'm driving. All right, so if we have our function, our original function is the position function, our derivative tells me how fast I'm going at a specific time. So I go from position to how fast I'm going, which is known as your velocity, your speed or your velocity. All right, and then if we do this again, we'll take, again, our output unit for our derivative is miles per hour. We divide that by our input, which is still hours. And we get miles per hour squared. And this one might not be as obvious. You don't use miles per hour squared in your daily life, whereas you do for miles per hour. I have miles per hour squared is your acceleration. It's how fast you're speeding up or slowing down at that time. All right, so this is a really important application. If we start with our original function being position, its derivative is going to tell me how fast I'm going at a specific time, and its second derivative is going to tell me how I'm accelerating at a specific time. All right, so this is the relationship between position, velocity, and acceleration. You just take derivatives to get from one to the next. All right, here it is in the phrasing. All right, so we start with position. If I take the derivative of position, that's the same as velocity. If I take the second derivative of position, that's the same as the derivative of velocity, which is the same as acceleration. All right, so we go from position at the start. We take a derivative to get velocity, which is how fast I'm going. And we take the derivative of that to get acceleration. All right, that's the only real three that get used in the AP exam. You can keep doing these derivatives and get more. For instance, if you did the derivative of acceleration, you'd get what's called the jerk, and you could take the derivative of that and so on. They start getting less and less useful as time goes on. So the big three that the AP exam is going to use is position, velocity, and acceleration. All right, so we're going to use these functions in order to answer questions, most of the time kind of like word problem questions. All right, so these are scenarios that come up a lot. So an object is at rest when, all right, so if we're trying to figure out when this object is at rest for some given position graph, what do we have to do? Well, an object is at rest when it's not moving. And if you're not moving, then you're not going any direction, which means your velocity is equal to 0. All right, so if we're trying to figure out when something's at rest, we're just going to figure out when is its velocity 0. Because if your speed, your velocity is 0, that means you're not moving at that time. All right, when is an object moving to the left or down? Well, if you think about the number line, the left is the negative direction. So if I'm moving to the left, my velocity is going to be less than 0. All right, and same thing for down. We're talking about straight line motion, so you're either doing one or the other. You're just moving kind of left and right, or you're just moving up and down. But if you're moving left or down, that means your velocity is negative, because you're moving in the negative direction. And that's really the only difference between velocity and speed. Speed doesn't care about direction, it's just how fast you're going at that time. Velocity has a direction, so velocity can be negative. And an object is speeding up. If you're speeding up, your velocity is getting bigger. All right, so we're going to say an object is speeding up if the velocity and acceleration have the same sign. And sign with the G, not the trigonometry sign. All right, so if velocity and acceleration have the same sign, because if I'm going this way, my velocity is positive, and my acceleration is also positive, that's going to pull my velocity even farther in that direction. All right, so I'm going to be speeding up because this positive velocity is getting a positive acceleration. All right, if I was going this way, to the left, and my acceleration pulls me farther to the left, then I get a velocity that's greater going to the left. So I'm speeding up. All right, the signs don't match. If I say I was going in the right direction, but my acceleration is in the opposite direction, I have a negative acceleration, well, that's going to cancel off some of that right-hand speed, and I'm going to get a resulting speed that's slower, so I'll be slowing down. So if your acceleration is pulling you in the same direction as your velocity, it's going to be pulling you faster and faster in that direction. If it's the opposite of your velocity, it's kind of pulling you in the opposite direction as you're going one direction, and it'll kind of cancel out and slow you down. All right, so when you're trying to figure out something speeding up, you check the velocity and acceleration. If they're going in the same direction, then you're speeding up. If they're opposites, you're slowing down. All right, so now we'll just answer some questions related to those things we just did. So we have a particle that's going along the x-axis, so it's just going left and right, and then we have a position. When is the object at rest? Well, to figure out when it's at rest, we need to figure out when the velocity is equal to 0. And velocity is the derivative of position. So the first thing I do is take the derivative of this function. I'm going to get 1/3 times 3 is 1. 5/2 times 2 is 5, plus 4. All right, so that is our velocity function, just using the power rule to take the derivative. And remember that the derivative of a constant goes away. And now we need to take this equation for velocity and run at rest if it's equal to 0. So now I just need to solve this equation. I can solve it using the quadratic formula, but this one also factors. And I'm going to get x equals 4 and x equals 1. So after 1, it doesn't give me a unit, so let's just say it's seconds. After 1 second, it's at rest, and after 4 seconds, it's at rest. All right, so remember this for our next question as well. All right, but at 1 second and at 4 seconds, my object is at rest. All right, when is the object moving to the left? So we know an object's moving to the left when its velocity is less than 0. Well, our velocity function we just had, our velocity function was x squared minus 5x plus 4. And we need to figure out when is this 0. All right, and this is a technique we'll use a lot throughout the semester. All right, this is a continuous function. All right, so we know if we have the places where it's 0, we just figured this out in the last question, at 1 and 4. All right, those are the places where it's equal to 0. And since velocity is continuous, let's just think if we had like a graph of our velocity. All right, and these are the places where it's 0. If I know my velocity is up here at the start, I can't suddenly jump down to being a negative because I have this continuous function. I can't jump. I had to go through that 0 to get to the other side. And same thing here. Once I'm down here, there's no way I can get back to being up here without crossing through the x-axis, and we know that happens there. All right, so we can use these zeros to our advantage. So the only places where I can switch from positive to negative. All right, this kind of relates to the intermediate value theorem, which we talked about a few units ago. But this is just a process we'll use a lot. We figure out where it's 0, and then use that to figure out where it's positive and negative. All right, so what we're going to do is we make this number line, all right, with the places where it's 0. So 1 and 4 are where it's 0. And then we just do test points in the other region. So for instance, I can start with a test point of 0, because that's less than 1. I can do a test point of 2, because that's between 1 and 4, and a test point of 5. All right, so these are places, well, let's just go through and I'll kind of explain why we're doing this. All right, so 0, I'm going to plug it into, I'm trying to figure out what is my velocity. So I'm plugging into my velocity function. I'm going to plug 0 into my velocity function. I'm going to get 4. Right. Which means at 0, since my velocity is positive, I am moving to the right. And based on this little graph I drew, if I'm moving to the right at 0, I can't start moving to the left until after 1 when I had hit that 0. I can't jump from moving to the right all the way to moving to the left without crossing through the x-axis. So if 0's positive and moving to the right, then everything else would have to be as well. If I plugged in 0.1 and 0.5 and 0.9, all those are to the left of 1. They're all also going to be positive and moving to the right. All right, next thing I'll do is plug in 2. That's going to be 4 minus 10 plus 4, which is negative 2. So when I plug in 2, I get a negative. That means I'm moving to the left. And because of this argument about having to move through the x-axis to change directions, that means everything else in this region between 1 and 4 is moving to the left. And the last one, 5, 25 minus 25 plus 4 is 4. And again, that's positive, so I'm moving to the right. Again, since that one value is positive, everything else in that region has to be positive because I can't change unless I hit the x-axis, which we know only happens at 1 and 4. So my final answer is moving to the left from 1 to 4. All right, so between 1 and 4, all right, that's the only possible time that I could be moving to the left. All right, my test point of 2 gave me a negative number, so I'm moving to the left at 2, but I had to be moving to the left in everything else in that region. All right, so this, again, is a technique we'll use a lot in the next kind of 2 units. All right, when we want to know positive or negative for sections, we figure out where it's 0 first, and then just do test points around those zeros. And one more example. When is the particle, at time 3, is the particle speeding up or slowing down? All right, so remember, this has to do with does velocity and acceleration agree? So we're trying to figure out if a particle is speeding up or slowing down. Figure out velocity and acceleration, do they agree? And again, it just depends if they're both positive or they're both negative. From we just saw, from 1 to 4, our object's moving to the left, so we know our velocity at 3 is negative. And again, you can just plug in 3 into the velocity function. If I plug in 3, 15 plus 4, see, it's 13, negative 2. Right, so our velocity is negative. And then we have to find acceleration. Again, remember that acceleration is related to velocity. I take another derivative, 2x minus 5. And I want to plug in 3, right, to know what my acceleration is at time 3. And I get 1. So my acceleration at time 3 is positive. So my velocity is moving in this direction. My acceleration is just positive, it's trying to pull me back in that direction. And since velocity and acceleration are different, all right, one's negative, one's positive, I'm slowing down, because I'm moving pretty quickly to the left, but my acceleration is pulling me back towards the right, so I'm going to be slowing down to slowly start going back to the right. All right, so this is kind of the applications that you'll have to do when you're dealing with position, velocity, and acceleration. When things are at rest, velocity is 0, left, velocity is negative, right, velocity is positive. All right, speeding up, velocity and acceleration are the same, and so on. All right, so these are the type of applications that you'll see on AP questions. All right, so in class, we're going to practice using our derivative skills in order to interpret scenarios. So we'll do some position, velocity, and acceleration things, and also just some general questions about if we have a scenario, what does the derivative represent? And now it's time to workshop some end of the video quotes. So for this one, I'm just going to say, keep going and keep growing.